Who was in my talk yesterday? My Unicode talk? Cool. Okay. So this is helpful if you came to my other talk. And, I could talk a lot longer than 20 minutes, but you don't want to have to do two 40-minute talks. So, okay, so this is partially about more VM, Unicode internals, kind of some basics, and also what I've been working on the last couple months. So hopefully it'll be interesting to everyone. Okay, so first I'm going to talk about the Unicode deflation algorithm. Talked slightly about it yesterday, but today I'm going to talk about how it was actually implemented. So you have the primary levels, with different letters, secondary, accents, tertiary, letter variations, or case. And so for all values, primary is larger than all secondary values, secondary is bigger than all tertiary values, and the value of 0 means you ignore it for that level, which basically means skip it, go to the next one. So, ignorable values mean 0. So that's not included in the greater than thing. So 0 just means it's ignored. I'm going to use this notation, primary, secondary, tertiary there. So different scripts have different concepts of case. Just so you give you a good concept of understanding it with the Latin example. In most cases, you have one code point mapped to one collation array, which is primary, secondary, tertiary. But in many cases, this isn't true. Single code points can and do map to single or multiple collation array elements. And sequences of code points can map to a single or multiple collation arrays. So some sequences can exist inside of others. So you may have XYZ be one sequence, but there's still an XY condition or just an X. So you have to look forward a couple spaces to see if you have a match when you counter some of the characters which are part of these sequences. So how do these collation elements translate into certain code points? So here, for two characters X and Y, I grabbed these from some random characters. So you see X and Y, right? It's not actually X and Y, but these values here, the collation algorithm is defined by Unicode. You take the primary. Let me see if I. Okay, so you take the two primaries, you push it onto an array, and then you put a level separator, 0, and then you take the secondaries, push it on another separator, and then do the two tertiaries. So that is the reference example. That's the reference standard. So that's less than ideal. We would be forced to traverse the entire string before making decisions. We'd be forced to start at the beginning of the string, and let's say if there was a 1,000 code point string, you just be pushing all these elements onto the array when you don't really want to have to do that. So the solution, instead, what I decided to do is leave the arrays as they were, which allows us to avoid having to copy it more locations. So keep it in the actual core data instead of changing them into a linear progression and having to do it for the entire string. So we go through each of the primaries. So this is the order that we check. So the data inside of it is going to have one of these. There's a stack, and the stack, each element has these elements. So we check the primaries, and if we run out of primaries on the stack, we grab some more from the stack. So that makes us only grab the collation elements as we need it to decide how a string is how it's going to be sorted. So that avoids doing a lot of work and a lot of copying of memory. That's always good. For the code points that are part of a sequence, I store, there's a quick check property, so I can check the code point that it sees and see whether it's a starter in one of the sequences. If it's a starter, I have to check the linked list, but otherwise it just grabs the values and pushes it onto the stack. So I explained the modified way that I do that, at least in general. So what about the start of the string? So I said how to prevent us having to read to the end of the string. How do we prevent having to push on all from the beginning? So if I have two strings, they might be the same for a couple hundred code points in, and we don't want to have to start at the beginning and push all those onto the ring. So I have a ring buffer of size 3, and if you don't know what a ring buffer is, essentially it just goes in a circular pattern. So you put a code point in here, put a code point here, here, and it just keeps going until it finds 2 code points that are different. Once it does that, it already has 3 code points in the buffer, and that length is determined by the longest sequence that are in the collation data. So then we go back to the first code point in the buffer, and we only have to read 3 code points before the difference of code points in each string. Yes, so I said that. Does anyone have any questions about that? No? Okay, I can go to the next part then. Okay, so I'm going to talk about strings and concatenation and how that happens in MoreVM and some of the improvements that I've done to that. So strings in MoreVM are stored as 8-bit or 32-bit signed arrays. Just normal C arrays. We have our own types, but that's where the actual blob data is stored as. Recently I made the change so that it starts trying to store the string as 8-bit, and as soon as it encounters a character that's too large, it will start putting it into a 32-bit array instead. What we did before is we would go through the entire string, put it into a 32-bit array, and if it saw only code points below 254, then it would convert the 32-bit string into 8-bit, which would cause a lot of unneeded memory allocation. So it's a lot better to start small and then get big again, because then we immediately know if we have to switch to 32-bit and we don't have to do twice the work all the time. So in MoreVM, we have a concept called ropes. Strings are immutable, and these ropes allow us to create new strings without having to copy all the data. So when we concatenate 2 strings, we have string A and string B, and we concatenate to become string C. So if A and B are just normal strings, totally flat data set, then what is created is a new string that is just references to string A and B. And that's much faster than having to copy the data around. And because they're immutable, if they weren't immutable, you might do something more complicated like move one, but they're not. So that's how we concatenate in a simple way. If we're able to, we just create a reference to the two and we're done with that. So what happens if we need to renormalize? Sometimes with Unicode, the 2 strings, it will change when the 2 code points, the last of string A and the first of string B, they might combine with each other, or they might not be in the correct order for Unicode canonical form. And so what we used to do is we used to just renormalize if there's a change that it might change. And recently I made a change. So it uses the same algorithm that we use for normalization. So that means we don't accidentally pass it through and renormalize it when we don't actually need to, and the string won't change. So, as I said, if the 2 graph names don't combine, we just proceed as I said in the last slide, just have references to string A and string B. Otherwise, we renormalize everything. But recently I thought there was a better way to do it, and I've been wanting to do this for a long time, probably as long as I've been a Perl 6 working on more VM. So it's cool that I was finally able to do this. So previously we iterated for string A and B, renormalizing it if the 2 code points would change. So that's not that nice. So with the new code, what we do is we copy the strands, so string A and string B in the concatenation, they might be composed of strands. So that makes it a little trickier when we have to, what we end up doing is we renormalize only a section of the string instead of having to renormalize all of it. So only the part which has to be changed in the middle, we grab that out of it, normalize that, and essentially we use the same method we used to create a substring, and we adjust the reference to string A and to string B to be 1 code point different. So then we end up with a rope that is 3 strings instead of 2. And then we avoid having to renormalize all of string A and B. So, yeah.
So a strand is basically a pointer to the character array plus the size.
Exactly.
Okay,
so
you can just reuse the same pointer, but take one less.
Exactly. So this links to the strands. We have a reference to the blob data. We have a list of how many graphemes it's composed of, and we have a list of where it ends and where it should start. So what we do is we adjust as I said, there could be multiple strands in the things we're concatenating, which made it kind of tricky because I would have to make sure to adjust the right strand. And strands could have been, sometimes there'll be 1 code point, and then it would be totally consumed. And our grapheme iterator doesn't like that when there's no code points in the strand. So it basically drops them from the rope if it actually ends up consuming the whole strand, which is actually more common than you might think. I mean, if something's at the edge, or it might just be a string of 2 code points and they end up combining, and then you consume A and B, and in that case, it actually just creates a brand new string and doesn't concatenate anything. So we cover that case and avoid doing any concatenation at all and just creating a new string of those 2 graphemes. Okay, so I talked about yesterday about fold casing and how our regex now, as of maybe 3 months ago, uses fold casing semantics instead of lowercase. So lowercase, it's guaranteed for the code point not to expand. You're going to get 1 code point if you lowercase something. It's not going to get any bigger. And so that made it more complex to find something when the size of the string ends up changing partway while you're reading it. So yeah, the needle and the haystack, both of them can change size. You can't assume just because one is longer than the other that you won't find one inside the other, because it could triple in size. The largest difference is the FFI ligature. It turns into 3 code points, so that expands a great deal. And so the 2 operations in our regex that were most important to do was index and EQ at, which basically means check if it exists at that point. So here's FA, the ST ligature, and you'd want to return 1 if you gave it an index of 2, 0, 1, 2, right there. And so this is 2 characters, but you're trying to find something at the very end, and there's not 2 there. So you have to make a lot less assumptions about where you might find it. And so there were some bugs that I introduced on accident where, because it assumed that, and it ended up, in certain cases, it would say it did exist there when it didn't, because I'm not going to go into it now, but now it is all perfect. Everything is all good. So, I realized that what we really want is for the index operation is the location based on the current haystack. So you want to be able to expand the haystack at certain parts, but still keep a reference to the start of the needle. And you can kind of you have to keep track of how many code points it changes, because what my functions do is it retains that information. Because I'm planning to add that into Perl 6. Because currently, if you match STA against ST, well, with case insensitive, it'll return 2 code points because it thinks there's 2. But what I'm going to have to incorporate the extra information that I already hold on to, but currently it's not yet implemented, to keep track of that and return the proper length of the string. And that's it. If anyone has any questions, be free to answer all of them.
I got a Korean question. Can you treat Hangul the same with the normalization tricks you did with the strands at the end? Because Hangul is a bit different than all the others.
Yeah, if it is different, it only if they just plain combine, but not in the other cases. So if it needs reordering, most of the time that it's not very likely that it's going to happen but it can happen. And so that's the only case where it actually does have to do the full renormalization. But on the test that I did, it decreased it by over 80%, the amount of times they would have to do the full normalization. So in normal, everyday cases, there's probably more than 90%. So that's a big improvement if you're working with other languages. Any other questions?
Information.
Even not a question, anything that you want clarification on or you're curious about?
Well, one little thing.
Yeah.
I take it there are edge cases should say concatenations end with an 8-bit integer and go to a 32-bit coupling on string B.
Okay.
Edge cases there as well.
So it's not really an edge case because you can have strands that are made up of partial on 8-bit sections and 32-bit sections. So all the strands in one row don't have to be the same number of bits. So it basically works as C integers, and so it'd end up doing the same thing if the strands have different number of bits per code point.
Okay, so it's effectively concatenate a sequence of numbers rather than trying to having a simple marker. I was thinking of something like along the lines of a shift distance coding where you have a marker indicating a switch from 8 to 32. So the 8 and 32-bit line is just part of the markers.
Okay. Yeah, I know it's a lot of information, but
It's fun. I used to do a lot of work with encoding, so I'm all too familiar with the ins and outs.
okay.
Thank you.